Hello everyone, in this video I will go over my solution for the problem named fixed point guessing taken from today's Codeforces round. This problem is an excellent interactive problem which teaches you exactly how you can use binary search, and that's what I'll be focusing on in this video. So in this problem we're basically given an array A consisting of n elements where n is odd. Now the jury has selected n-1/2 disjoint pairs of elements and has swapped those elements. So initially the array A is the identity permutation, and then the jury has swapped n-1/2 pairs. So since n is odd, one number remains exactly in its place. So for example, if A is 1, 2, 3, 4, 5, and he has swapped the pairs 1, 4, 3, 5, then the number 2 remains in its place, and we need to find out this element which does not change its position, because we know that if there are n-1/2 pairs of elements which are swapped, there are n-1 elements which are changing their position, and hence one element is not changing its position. So we need to find that element. In order to find that element, we can ask queries of the form L, R. You output L, R, and in return you'll get the elements of the subarray AL through AR sorted in increasing order. So we need to use these kind of queries, at most 15 of those queries, in order to determine which element is missing in the array. So this problem is actually a simple binary search problem once you understand how the check function works, and the binary search part of it should be clear, what we are binary searching on, and why binary search should also be clear. This number 15 obviously tells you that for n is 10 power of 4, 2 raised to 15 is approximately 10 power of 4. You don't even need to calculate that. So that's like 2 raised to 10 into 2 raised to 5. So that's about 30,000, which is a little more than 10 raised to 4. So obviously binary search is the way to go for this interactive. And since that's very obvious from the constraint itself, we only need to figure out exactly how we can do the binary search, and that's exactly what is the most complicated part of the problem. And initially this was C in the contest, but we moved it to D because not many people were able to get the check function for the binary search part of the solution. So let's discuss the binary search. The sample, there's not really much to consider. You can only figure out the format of the input and output, which you should know for interactives. So you can pause the video and figure out how the input and output works. But I'll be moving straight to the binary search part of the solution. So we know that in order to binary search on the missing element, so we are binary searching on the missing element. That's obviously the first step, binary search on the missing element. And in order to binary search on the missing element, let's say that we are chosen the range L to R. So let's say that the binary search range is L to R. What can we possibly do with the range L to R? So how can we figure out whether the range L to R, whether the element appears in the range L to mid or mid plus 1 to R? That's what we want to do with the binary search, right? We need to figure out in one query whether the element which is missing lies in this half or this half. Now notice that by range, I mean the range in the array. So I'm not talking about the range of the numbers, I'm talking about the range of the elements. But it should not really matter whether it's the range of the numbers or the range of the elements, because we know that A of I is equal to I for the missing element I, and hence whether you're binary searching on the range of numbers or whether you're binary searching on the range of indices, they should be similar. But for simplicity, let's binary search. L, R represents the range of indices. So left endpoint of indices, which you are binary searching on, left endpoint of range of indices, and R represents right endpoint of range of indices. And we know that the correct index will be the index I, such that AI is equal to I. So this is for the missing element I. And now let's try to formulate a check function which will utilize the property that when you query for a range, so let's say you're querying on L to mid, so let's say you call the query method L to mid, then what query L to mid will return is the sorted version, so the sorted subarray from L to mid. And how exactly should we use the sorted subarray from L to mid? That's exactly what the problem reduces to. Let's use the fact that we know that the elements from L to mid is this sorted subarray. So let's call this S for example. So let's say S is the sorted subarray from L to mid. We need to use S to determine whether or not the missing element is contained in this range L to mid. So let's say we can determine that from this sorted subarray. Let's say we are somehow able to magically determine that the missing element is contained in this sorted subarray. If we are able to determine that, then we can just binary search on L to mid. Otherwise, we know that we should binary search on mid plus 1 to R. So that's the simple logic behind the binary search on the missing element. Now let's try to find out exactly how we check whether this sorted subarray will contain the missing element or not. So in order to better understand the solution for the query, let's look at an example in which we have the array 1, 2, 3, 4, 5, 6, 7, and we swap the elements 1, 3, 2, 6, 3 and 1 are swapped, and similarly 6 and 2 are swapped, 4 and 7 are swapped, and 5 is the identity element. So the key idea is that when you look at any subarray L to R, and if you look at all the elements appearing in that subarray, so let's consider an example. Let's say that the subarray is from 2 to 6 or from 2 to 5. Let's consider both subarrays. So if you look at the subarray from 2 to 6, and if you look at all the elements, then in the subarray from 2 to 5 first, in the subarray from 2 to 5, you will see that the elements which appear are 2, 3, 4 and 5. And in the subarray from 2 to 6, the elements the elements which appear are actually not 2 doesn't appear because 2 has been swapped. The elements which appear are actually going to be 1, because on the second index 6 appears, so 6 appears first. Then the number which appears at the index 3 is 1, the number which appears at index 4 is 7, and the number which appears at index 5 is 5. So these are the elements which appear in the sorted version. And similarly, if you consider 2 to 6, all these elements appear, and additionally at position 6 2 also appears. So these are the elements which appear in the range 2 to 6. And if you consider another range, just for example, from the range 1 to 3 or the range 2 to 3, then in both the cases the ranges, so basically I'm considering ranges which include the element 5 and which do not include the element 5, and I'm trying to give an intuition behind what is the difference in these ranges. We know that the range 2 to 5 contains the element 5, and 5 is the identity element. So these two ranges should have something special about them which differs from the ranges which do not contain 5. That's what I'm trying to give you the intuition about. So let's look at the ranges. When we look at the range 1 to 3, we know that the elements which appear are 1, 3, 1, 6 and 3, because 2 has been swapped with 6. And then if you look at the range 2 to 3, the elements which appear are 6 and 1. So over here, sorry about this, this should be 3 and this should be 1. And I think this is the sorted version for the ranges 1 to 3 and 2 to 3. So let's try to figure out exactly what is the difference behind these two crosses and behind these two ticks. So in these two ticks, you will realize that if you consider the elements appearing in 2 to 5, and if you consider the numbers 2, 3, 4 and 5, then what you'll realize is that in the numbers 2, 3, 4 and 5, among those numbers, only 5 appears over here. So the count of numbers, in range 2 to 5 which appear between indices 2 and 5, between indices 2 and 5 is odd for the tick ranges and is even for the cross ranges. That is essentially what the observation is. And I'll be explaining in a bit why exactly that works. But let's look at the other examples. So this is the first example where the count of the numbers in the range 2 to 5 is exactly once, because only the number 5 appears in the range of indices 2 to 5. So this is odd. In the next example, where you have the range 2 to 6 and the elements are 6, 1, 7, 5 and 2. So in this example where the range is 2 to 6, we know that the count of numbers in range 2 to 6 which appear between indices 2 and 6 is odd and is equal to 3, because the numbers 6, 2 and 5 are the three numbers which appear in the range 2 to 6. The reason why it's odd is because the number 5 can appear because it's the identity element. However, all the other numbers which appear have to appear in pairs. So both 2 and 6 are contained in the range, so they appear in pairs. In the previous example, 2 and 6 were both not present. When you consider the range 2 to 5, 2 was not present, 6 was present, but it is not counted in this range. And in general, it will always be the case that the numbers which are swapped will always appear in pairs in the range, and the identity element will be the only single element which will make the count odd. So if you consider the other two examples, you will realize that the count is even, because count of numbers in range 1 to 3 which appear between indices 1 and 3 is exactly equal to 2, which is even. So that's why they appear in pairs again. 1 and 3 appear in pairs, and the count of indices in the range 2 to 3 which appear between the count of numbers in range 2 to 3 which appear between indices 2 and 3 is again is 0, which is an even number. So that's why we can clearly see that all the numbers will appear in pairs, or they'll appear 0 times, and except for the identity element, which will contribute to a +1 in the answer. And hence, if you want to look at it formally, a good way to say this would be the contribution is even for all pairs of elements, because they either both appear or both do not appear, because they either both appear or both do not appear in L to R, in the numbers from L to R, or in the indices from L to R. So they will either both appear in L to R, or they'll both not appear, like in numbers from L to R and indices L to R. Now what this means is that +0 or +2 will be the count will increase by +0 or +2. So that will be the change in the contribution, will be the delta in count for each pair. However, for the lone element, for the identity element, the element which remains the same, the contribution will be +1, and hence we know that the identity element will cause the parity to change to odd. Otherwise, it will always remain even. Whether you add plus 0 or plus 2, the sum will always be even. However, when the range contains the identity element, the parity will change to odd, and that's why what you essentially need to do is, for the range L to mid, check whether the count of numbers which appear in the range L to mid, in that subarray from L to mid, if that count of numbers in the range L to mid which appear in the subarray from L to mid, if that count is odd, we will binary search on L to mid, otherwise we'll binary search on mid plus 1 to R. And now I'll show you the code which implements the same idea. So the code is actually very short because the query is the main part, otherwise the binary search is very simple. The query is the most tricky part, which should take you the most time to understand, and I understand completely if you have doubts, because the solution can still seem very sketchy, but like leave the doubts in the comments below on exactly where you're confused, or whether it's the query function or the binary search in general. So again, explaining the query function in brief, we are counting how many numbers in the range L to R appear among the indices L to R. So for each index, therefore for each index I going from L to R, if uh, if if the number x, so for each index I going from L to R, if the number x is equal to AI lies in the range L to R of numbers, then we increase count by 1. So that's what we are counting. The count basically represents how many numbers in the range L to R appear in the subarray from L to R or between the indices L to R. So this is actually the subarray from L to R. So for each element in the subarray from L to R, we are counting whether or not it lies in the range L to R of discrete numbers. So if that is true, we increase the count by 1, and in the end we just return whether or not count is odd or even. So if count is even, we return 0, otherwise we return 1. And basically over here in the binary search, if this count is 1, we know that L to mid contains the identity element, because we know that the identity element is the only number which can cause a plus 1 uh, and cause the sum to be odd. Otherwise, all the other elements appear in pairs and cause a delta of cause an even delta essentially. And the reason behind that even delta, you can see from examples and from the diagram, that when you swap the elements, you're swapping the elements such that both the elements are either in the range or out of the range. And you should pause the video and go through many examples of the subarray in order to understand when the count of the elements which appear in the range L2R and which appear in the subarray L2R, when is that odd and when is that even. And you will notice that whenever the subarray contains the identity element, only in those cases the count of numbers in the discrete range L2R appearing in the subarray L2R, only then the count is odd, otherwise the count is even. So that's how the binary search works. And in the end, we just keep setting mid as the answer, because we know that the somewhere in the range L to mid the identity element lies, so we might as well just set it to mid, or you can also set it to L. It doesn't really matter. Both ways, the final answer will represent the mid value or the L value. And now I'll just submit this code to check whether the binary search works. So actually you should set the answer to be equal to mid. If you set the answer to be equal to L, you'll get a wrong answer. So you can experiment with this and try to find a test case where this fails. But in general, like in the binary search, we always set it to be mid. So to be safe, you should use mid. And of course, in the actual contest, you can try both and see which one gets accepted. But this is the full solution. And the key idea behind the solution is to figure out how many elements which appear in the discrete range L to R also appear in the subarray from L to R. And if you know that count, you can find out the parity of the count. And using the parity of the count, you can deduce when that is odd, the answer will lie in the range L to mid. Otherwise, the answer will lie in the range, will lie in the other range, which is mid plus 1 to R. And that's why we can use binary search effectively. Obviously, the giveaway for binary search is this 15 queries for n is 10 power of 4. But otherwise, also, you should just knowing that binary search works is not enough to be able to get the full solution for this interactive problem. So I hope you like this problem and my solution. If you have any doubts in any part of the solution, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.